So far, everything covered has addressed an ideal oscillation where we have frictionless surfaces, where we don't have any losses and the mechanical energy is conserved. Of course, that doesn't really happen in a real oscillation. In real oscillations, sometimes there are dissipative forces, sometimes there's air resistance, sometimes there's friction. One good example might be a shock absorber in a car. When you drive along in your car and you hit a bump, car starts to bounce up and down a bit, but that bouncing dies off really quickly. That's because there's oil in your shock absorbers that makes that oscillation die out quickly. So the real oscillations, which don't continue forever, they're called damped oscillations. And a damped oscillation is an oscillation which runs down and eventually stops due to some resistive or dissipative force. And that's characterized by a damping coefficient. It tells us how fast does an oscillation die off. So a real oscillation, the kind of graph we've looked at so far, has x equals a cosine omega t, and these things don't change. A doesn't change, omega doesn't change. And this oscillation will continue forever. A real oscillation, however, a damped oscillation, will still start at an amplitude or some value offset by a phase constant, and it will oscillate up and down, but every time it oscillates, it won't quite go as far as it did before. So when it oscillates down, it won't quite reach the negative amplitude. When it comes back up, it won't quite get back up as far. So as it oscillates back and forth, it goes less and less far every single time. So that's one thing that happens. The amplitude of oscillation over time decreases. And the other thing that happens is that the angular frequency also changes. So two things happen here. So amplitude decreases, and the period increases. So the time for one oscillation increases, or the angular frequency omega decreases, fewer oscillations per second. There are lots of equations to describe this. I don't think I'll write it down because I'm not going to go through an example with numbers. The decrease in amplitude, that is an exponential decrease. So maybe I'll just pop in that equation and we'll call that good. So the amplitude, you might call that x maximum, is equal to the original amplitude times e to the minus b times t over 2m. So b is that damping coefficient. It tells you how fast it's going to die off. T is the time, m is the mass. So that maximum possible value dies off over time.
So here's a good question. Is a damped oscillation a good thing or a bad thing? So often when we're doing physics problems, we neglect air resistance, we neglect friction, we assume the ideal situation. Um, but is a damped oscillation necessarily a bad thing? I would say definitely 100%. A lot of times we need a damped oscillation. So a good example is a dance floor. So if there's a whack of people and they're out dancing really energetically to a music with a strong beat, you can set up an oscillation in that dance floor. You can make it bounce up and down. You probably don't want your dance floor to bounce up and down too much because eventually it will start to show strain and could break. So what engineers do when they build structures like dance floors and bridges is they build damping into the structure to make the oscillations die off. So it makes for a safer structure if we have a damped oscillation.
Now, the very last bit we'll discuss is a driven oscillation. So think about when you're on a swing, if you want to get going nice and high, you have to pump your legs at exactly the right time. If you don't pump them at the right time, you're not going to get any motion at all. So that's a driven oscillation. You push an oscillation at exactly the right speed, at exactly the right frequency, and you end up getting a large response. You get a big amplitude of motion. So let's look at a couple of examples. The first one, I don't know if you ever watched a cartoon when you were a kid of an opera singer shattering a wine glass. That's a true thing that you can totally do. Okay, now that wasn't an opera singer, it was just a stereo speaker playing a certain frequency. But when that frequency hit the right frequency, the edges of the wine glass really wobbled a lot until it actually broke. So apparently that's what some singers can do. I can't hold a note, so I've never been able to do it. If any of you listening are great singers, can hold that pure note, maybe give it a try. Could be kind of fun. Okay, now here's another example that maybe you seen before if you've done high school physics.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
I think I disagree with our narrator's version a little bit. I think the poor little doggie's owner and the doggie himself must have been very sad at that. Okay, so there is some fact versus fiction about the Tacoma Narrow Bridge. Um, it's often presented by saying that the wind was blowing to cause the vibration, puff, puff, puff. That's not actually what happened. The wind blew rather steadily, and the wind caused a transverse vibration. It did make it vibrate a little bit, but that wasn't strong enough to cause the collapse. There was also a torsional vibration. So the right side of the bridge went up while the left side went down. That caused some internally excited vibrations called aerodynamic fluttering. It's really complicated. However, the wind did set up this resonance the way that it happened, and that's what caused the bridge to collapse because the oscillations were so large that the structure couldn't keep up with it. One other story is the Brighton Suspension Bridge. So that was a suspension bridge that soldiers trooped across in the 1800s. And what happened when the troops went across the bridge, apparently it induced a mechanical resonance by the soldiers marching in step, 1, 2, 3, that sort of marching rhythm. So after that, and I think this sign is still there is an order that all troops have to break step when they go across the bridge so that they don't end up causing the resonance and making things collapse. So this circles back around to our damping. All of these ideas are really important to engineers. When we build structures, they have to be built, first of all, with natural frequencies that don't match prevailing conditions. So if you're building a bridge, you have to do a wind study. You have to know what the wind is, which way does it blow, and what is the general speed. You also have to build damping into your structures. You don't want your bridge to explode, and one way to prevent the resonance is to have damping built right in. So that will stop the resonance in the bridge. So now here's just a summary of some of the things we were talking about. The driven oscillation is the motion we get when we apply an external periodic force. The natural frequency is that just right frequency that we have to hit in order to get resonance. And resonance is what happens when we do drive it with the natural frequency and we get these large amplitudes of oscillation.